Imagine we have an object, has a mass, call it m1, and it's launched with a velocity v naught at some angle theta above the x-axis. Now we should define our coordinate system. Left and right be the positive and negative y-axis, x-axis I mean, and up and down will be the y-axis. Now this object has momentum and mass, so it has some, or velocity and mass. So it has some momentum, v naught, which is its velocity scaled by its mass. And since that's a vector, we can draw it like that. And because it's velocity scaled, it will have the same direction. And it has a horizontal component and a vertical component. We can find the magnitude of that horizontal component using trig. P naught x equals P naught cosine theta, or subbing in P naught m1 P naught cos theta. But this part is equal to the horizontal component of this velocity. So we can say that the horizontal component of momentum is the horizontal component of velocity scaled by mass. And there's also a vertical component of velocity. And we can do the same thing for the vertical component of momentum. It's P naught sine theta, or it's that vertical component of velocity, P naught y times m1. Now this object is going to start right here. Say t naught equals 0, and it starts at a position x0 meters, and it's going to go up a little bit. It's going to get to some highest spot here at time t1. It will have traveled along the ground a distance of x1, and it comes back down. Ends right here at xf after a time f. Now we want to use this idea of momentum to find the time it takes for our object to reach this highest spot and where along the ground, or what its horizontal displacement is at that spot, and then the time it takes to fall back down to the ground and where it lands. So we'll come over here and draw a free body diagram of our object. Here's our object. There's one force on it, straight down. That is Fg, since it's on Earth. And there are no other forces on it. There's no air resistance, nothing else. So our net force is Fg. And at any time during that path that it takes, Fg, straight down, is the only force acting on it at any spot on this path that it takes. Then we have Newton's second law that says F equals ma, or we can rewrite it, A equals net force divided by mass. But we're going to be using the other definition of Newton's second law that says net force is also the rate of change of momentum, or change of momentum is the integral of net force over time. And we can compare these two equations, these two definitions, with their dimensions. So MA is kilograms meters per second squared. dP over dt is kilograms meters per second, or that simplifies to meters per second squared. We'll come back up here. Right here, it's moving that way. Right here, it's moving that way. So right here, it's got a velocity to the right, horizontally to the right, since before it's going up, 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 it's here. So it's coming down, so its vertical velocity is going up before, then it stops. So there's 0 vertical velocity here, then it's coming down, which means its momentum at that point is completely in the horizontal direction. And then P1y equals 0. Now we'll come back to this equation we found, and we can find the change. Oh, we'll come back here. The change in momentum is a vector, and it's the net force scaled by time. So its direction is in the same direction as net force. So the direction of our change in momentum will always be in the vertical direction, meaning our horizontal momentum is constant. There's no change in momentum in the horizontal direction. And any change in momentum we experience will be change in the vertical direction. Coming back up here, we can calculate our change in momentum by finding our change in vertical momentum. So that is delta P equals P1, P1y minus P naught y. P1y we just found was 0. So delta P as a vector equals P naught y, but in the opposite direction, which is what the negative sign denotes. And the magnitude of delta P is equal to P naught y. Then we can say delta P equals P naught y equals the integral from P naught equals 0 to T1 of our net force, M1g, is what Fg is equal to, over T. Now M1g is constant, so we can pull that out. M1g times the integral from 0 to T1 of dt, which is equal to M1g times T1 minus 0, which gives us P naught y equals M1 g T1. Now we want to use this equation to solve for the time it takes to reach the time it takes for our net force to give us a change in momentum equal to P naught y, which will be the time at which our object is at this point. So we can substitute our equation for P naught in terms of mv and theta. Get m1 P naught sine theta equals m1 g T1. Now m is multiplying both sides, so we can cancel that out. Now we solve for t by dividing both sides by g. We get T1 equals g equals v naught sine theta over g, or v naught y over g. Now we have the time taken to reach this point. Now we can use this idea that our momentum in the horizontal direction. So now we're interested in its horizontal displacement after that amount of time. So we can come over here and see that because our horizontal momentum is constant, our horizontal velocity, which is this term, is constant because m is also constant. So we can say that delta x, this is using kinematics, equals b t, or x1 equals b naught x t1. And then we could sub these values, b naught x for this and t1 for this, if we felt like doing so. Now, we want to find how long it takes for it to fall from here down to here and where it falls. So we can use this idea, except our velocity is changing and we're looking at vertical velocity instead, vertical displacement. And we can say delta y equals the integral d dt, and then v, well, if p equals mv, we can say v equals p over m, and delta y equals the integral of p over m dt, or because m is constant, delta y 1 over m times the integral of p dt. Now we have two snapshots, or two intervals. We go up here, and from here up to here, and we have a delta y going up. Then we come back down, and we have the same delta y. So with the same magnitude, that is. So delta y is the same for both of these intervals. Mass is the same for both of these intervals. And then p here is a function of time based off of this relationship. So we could sub in this equation to p here, and then we would get p as a function of time. And then the only way for, so then if we have delta y equals 1 over m times p of t dt, and p of t is also constant, or the same starting at both of these intervals throughout the entire interval, then the only way for this entire expression to be constant, to be equal, going up and coming down, is if the time interval, the bounds of integration, are the same as well, which then tells us that the time it takes to go up is equal to the time it takes to go down. So TF then is equal to 2 times T1. And the position here, XF, using this same idea, and still constant horizontal velocity, equals 2 V naught T1. Or 2 XI. So we have xf, x1. And we could get this same result using kinematics. As we know, this motion is parabolic. So the time it takes to go up, it's the same as the time it takes to go down, since it's symmetric. Although we got there using momentum instead. Now imagine our projectile. It goes up, it gets here. Then right here, instead of continuing as normal, it explodes into two pieces. 2 and M3. M2 gets launched backwards with some velocity, and M2, surprisingly, lands right back where it started. M3 gets launched forward and lands way over here. And it gets launched with some velocity v3. Now we have two objects, or two pieces of the original object, and each piece has momentum. M2 has momentum equal to M2 v2. 3 has momentum equal to M3 v3. But what's their total momentum? Well, we'll go over here and look at before they exploded. Right before they exploded. So the instant before, we have M1. Then they explode. Right as they're exploding, during the explosion, M2 exerts some force on M3, and M3 exerts some force on M2, which pushes them apart. And this force, we know from Newton's third law, has to be equal in magnitude. Both of these forces have to be equal in magnitude and opposite in direction. And we can also say that because these pieces explode together, M2 exerts the force on M3 for the same amount of time that M3 exerts the force on M2. So we'll come back up here, say that dP equals integral of net force over time, except instead of that, we'll be looking at change in momentum from some component of force, which is these forces, and we get the change in momentum during this explosion, from this explosion, of 2 equal to F2 times some time, the magnitude, and then F2 is equal to F3 in magnitude, and they're in contact for the same amount of time, equal to the magnitude of the change in momentum of the other mass. So both of these pieces have the same magnitude of change in momentum from the explosion, not from gravity, and opposite directions. So if we draw a vector addition diagram, this one looks like that, or like that. This one looks like that. We add them together, and they add to 0. So the net change in momentum between these two pieces during and from the explosion is 0, which means, and that's the change in momentum from before the explosion to after the explosion. So if at m1, if right here, m1 has some momentum, then over here, the momentum of m2 plus the momentum of m3 has to equal the momentum of m1 because there was no change in momentum between m2 and m3. So we can say the momentum was conserved over that explosion, which means P3 equals P2, and P3 is the momentum of, or my bad, P1 is the momentum of the piece right before it explodes, equals P2 plus P3. Now P1 is m1 times the velocity. We'll use the same v1 right here, right before it explodes, equals, now we need to refer to our coordinate system. To the right is positive x, so P30 is positive. For P2, we should start with. P2 is to the left, which is negative, so minus m2 P2 plus m3 P3. Now we want to use this equation to find the velocity of these pieces and where this piece lands. Let's say we know m3 weighs 3 times as much as m2. So m3 equals 3 m2. And we also know m2 plus m3 equals m1 since they came from the same piece. That can tell us that m1 was split into 4 parts. So m3 equals 3/4 m1, and m2 equals 1/4 m1. Now we can substitute that into our equation. m1, v1, since we're interested in velocities only and not masses, equals negative 1/4 m1 v2 plus 3/4 m1 v3. Now we can come back up here and use this same logic down over here to determine that in order for m2 to have the same vertical displacement and horizontal displacement, it must fall in the same amount of time from here and then have the same horizontal velocity from here, which tells us that v2 is equal to v1, but in the opposite direction, or the magnitude of v2 is equal to the magnitude of v1. So we have m1 v1 equals negative 1/4 m1 v1 plus 3/4 m1 v3. Now we can solve for v3. We can add this term to both sides. m1 v1 plus 1/4 m1 v1 is 5/4 m1 v1 equals 3/4 m1 3. Now m1 multiplies both sides. We can cancel that out. m1 over 4 multiplies both sides, so we can cancel it out. And we are left with 5 v1 equals 3 v3, or v3 equals 5 thirds v1. Now the distance xf travels from this position, from x1 to xf3, its displacement from here is then delta x equals vx v3 p, and we use the same logic again to say that that m3 takes the same amount of time to land, so t is again equal to t1. Then we have delta x equals 5 thirds v1 t1, or because v1 t1 is equal to xi, we can say delta x equals 5 thirds xi. But then we have to remember that's the displacement from xi to xf3. So this position, total displacement from 0 to xf3, is 5 thirds xi plus xi equals 8 thirds xi. Now for grins, we'll look at the center of mass of the two pieces after they land. We have a formula for center of mass. The position of the center of mass along an axis, we're looking at the x-axis in this case, is the sort of a weighted sum of the position of each of its members, each of the system's members. So we have the sum of each mass member times its location divided by the total mass. And for our system of two objects, that is didn't mean to do that. Bear with me. There we go. Okay. So the center of mass is then m2 times 0, since it's at position 0, plus m3 times 8 thirds xi, all over m2 plus m3, which is equal to m1. Now m3 we found is equal to 3/4 m1, so 3/4 m1, and this is 0. So we have x, position of the center of mass, is 3/4 m1, 8 thirds x1, all over m1. m1 cancels out. Then we get x, center of mass, equals 24 over 12 xi, or 2 xi. which turns out to be this position. Suppose I should annotate this right here. And surprisingly, if we were to do that same process again for other times, maybe a little bit after they explode, we'd find the center of mass to be here. Then again, maybe a little while later, the center of mass is here. Maybe we do it here. The center of mass is over here. And it turns out that the path the center of mass travels is the same as if the projectile did not explode at all. So the path the center of mass takes, the path of the center of mass of the two parts of the projectile, is the same as the path of the projectile if it did not explode.